All right, only got one email asking to go over a question in advance, and this is for organic, and this is the last question, question 8, which talks about the 4 chiral centers. So you got the molecule R, 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 R. And we're just going to treat this as a hypothetical molecule. So we have a molecule with 4 chiral centers, chiral 1, 2, center 1, 2, 3, 4, and the person who asked the question, they are correct. We have 4 chiral centers, and so we have 2 to the 4 potential enantiomers. So in this case, we should have 16 when we finish. So the question is, how do you approach this problem? Well, the first thing is we're going to assume there aren't any meso complexes because we don't know what the molecule is. So we're going to assume we can get up to this potential 16, recognizing that this number could come down if there's meso. But again, you're not given the molecule, don't make that assumption. Now, you're asked to pair up all the enantiomers and diastereomers, and by definition, the enantiomer is one that has all the chiral centers changed. So the enantiomer of the 4 R's are the 4 S's, and this is our first enantiomer. So a diastereomer is one where only one center is changed, or one, but not all of them. So in this case, we could switch the first one, R, S, R, R, and its enantiomer is R, S, S. So there I'm up to 4. I could change the second R, R, S, R, R, and its enantiomer is S, R, S, S. I could change the third R, 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 S, R. This gives me S, S, R, S as the enantiomer. So I'm at 8, I'm already halfway there. And that's pretty much what you're going to do with this is you're going to iterate these. You're going to start changing the R and S's until basically once you get to your 16, that's when you're done. Now you may sit back and say, well, how do I know? Well, you go back and check. But what you're going to find is that this follows the reverse pattern. This is all 4 S's. This is one of them changed. Second one changed. Third one changed. I can do the fourth one changed, R, 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 S, and get S, 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 R, and so forth. Now we have 2 changed, S, S, R, R, so it gives us R, R, S, S, and so forth. And once you get to this pattern, once you get to your 16, if you go back through, you'll start noticing that how you would iterate it next starts showing up on the enantiomer side. So that's how you approach number 8. You write the 4 R's out, write out the enantiomers, and then you start changing one of the chiral centers, but not all the chiral centers, to come up with a diastereomer, and you match it with its enantiomer by switching all the chiral centers. So that's it in terms of the questions I got asked. It just came out of a meeting, so I actually need to respond to some emails. But I do have the chat menu open. Again, keep in mind there's about a 45-second lag from when you type to when I see it. So I am here. I may not immediately respond to your question. That's because you're just kind of seeing the lag and the latency of doing this by YouTube. So I am here. Feel free to ask questions. These are office hours. These are not lectures. These are not lessons. But if you have questions for Chem 1, Orgo 1, Chem 2, Orgo 2, any questions are welcome in the discussion. Right. So a question got to ask, what's the difference between cis and trans, and what's the key indicator? So cis and trans are going to fall underneath the stereoisomer umbrella, but they're stereoisomers because we don't have conformation available to us, so we don't get rotation. So they are not chiral centers per se. We can definitely create cis-trans configurations which completely lack this, and this is going to show up a lot with alkenes. The big thing though is that we can't rotate. So because we can't rotate, we kind of can't. If we could rotate, we wouldn't have these issues. So an example of this, if I drew this molecule here, and I can build it here for you with my model kit. This would imply by drawing these wedges that, here we'll do these two colors, that red and blue here are always, I've got, I'm sorry, blue and yellow. Blue and yellow are fixed, but I can definitely rotate around this bond, so this is kind of only true if the molecule is in that direction. But let's say I build cyclohexane. And I add my two atoms. Well, now they can't rotate, so there's really no way to get them onto the same side of the ring. And this is an indication of cis-trans. Basically, we lose conformations. We lose the ability to do a conformational isomer, or ability to rotate around a single carbon, single bond, because either we're in a ring or because we got an alkene. So cis and trans, these are not German in nature. Cis is same side. And the way I was taught it, the way it helps me to remember, this is a C shape. Trans are opposite. So something like transatlantic is across the Atlantic Ocean, trans-Pacific is across the Pacific. A trans group is opposite each other. Now, there is a restriction on this, which is why cis-trans is kind of limited. They have to refer to the same group. So the cis-trans here refers to the same group. So in this case, we have two methyl groups, and opposite them we have two hydrogens. So I take my molecule, I've got the two methyl groups and the two hydrogens, and both groups are cis. Now, I could put a branch off of this, so I can have the ethyl methyl. And with the ethyl methyl, I can still use the cis-trans because we still have two hydrogens, so the hydrogens are still cis. But let's say I throw something like a halogen on there. Or, yeah. So I have two yellow groups on the same side, and I've got this ethyl group, and I got this hydrogen. In this case, we're going to switch to the EZ notation. We'll talk about that more when we get to naming alkanes. But again, the tip-off that you need to use cis-trans if you've got a ring or you've got an alkene, and they're simply referring to how two groups are relative to each other's space. If they're on the same side of the ring or the same side of a double bond, they're cis. If they're on opposite sides, they're trans. Again, we're not going to quite emphasize that yet. We're going to get to that a lot more with alkanes. All right, other questions out there? All right, so I'm going to just turn the camera back off. All right, so next question I got asked is about converting a 3D drawing to a Fisher projection. And personally, this is something it took me about a year teaching organic to get to the point I could start doing in my head. So if you go like, this is really hard to do, yeah, because it really is that hard to do. So let's take a look at the discussion board question. So on the discussion board, you're given this. Now, there's a lot going on with this problem in terms of getting assessments. First thing is that a lot of students mistakenly think that because they see a stereocenter, they see a wedge bond, that implies a chiral center. That's not true. All chiral centers you have to designate with wedge or dash, but just because it's designated wedge or dash does not mean that it's a chiral center. So, the big thing I've seen on discussion boards I've been grading is people are calling this stereocenter chiral. And it's not, because this is a CH3 and this is a CH3. So by definition, chiral carbons can't have two of the same groups. First one's achiral, achiral. This one's chiral, this one's chiral, this one's achiral, and this one's definitely achiral. So you only have two stereocenters here. So how do you draw it? Well, the easiest thing to do is actually just build it. So we've got 1, 2, 3, 4, 5, 6 carbons. And if I take my molecule, I've got the top one coming out, the bottom one coming out, and the top one coming out. So this is my molecule as drawn on the board. I've got red, yellow, blue here. I know it's all in blue, but here I've got these carbons. And you, hopefully, if you pause the video, you can kind of see how it matches up with the molecule behind me. So the way we convert this to a Fisher projection is we take the backbone now, and we're going to bend it into a circle. So this is now how the Fisher projection is really what it's really showing. So to start my Fisher projection, I'm going to draw a vertical line, carbon 1, carbon 6. I don't really need to include them. I could put a cross and then do H, H, and H. There's nothing wrong with that. It's just that we know that those are achiral carbons. And the point of a Fisher projection here is to see the chiralities. So we're just going to kind of leave it off. If we do the first carbon, we have H, CH3, this is carbon 2. Carbon 3, we have, I guess I should show how I knew that. So if I start with this top carbon, and I start rotating down, if you look, I've now got the carbon hanging off to, actually it's the left side, I'm glad I did that. So I got a CH3 on the left, and an H on the right. Now I'm going to keep rotating. So if I rotate up, now I'm to the second carbon, the yellow here, and I've got the carbon on the other side. So now I've got it on the right side. So CH3 on the right, hydrogen on the left. Keep going. I move up to the next one. I've got the carbon on the left and the hydrogen on the right. And 5 has 2 hydrogens, so it doesn't matter. So if you were trying to guess chirality off of the wedge bond and you look at this, you'd see that there's 2 CH3 groups here. So this one's automatically eliminated as a possibility for a chiral center. And this gives us the third and fourth carbons where we don't see any mirror images. And we can definitely see that there are 4 groups attached to each carbon. So this carbon has a hydrogen, a CH3. This group, this carbon has a CH3, a hydrogen, this group, and this group. So definitely when drawing the Fisher projections, if you're having trouble just taking that visually and converting it, don't. Build the molecule. You will always have the modeling kits at your disposal. So once you've built your model, take it, bend it into a coil or a loop. Arbitrarily pick one end of the loop to start on. In this case, I just prefer to keep all my groups at the top. And then start with the top and start working your way around the circle and just start drawing what you see. So if you see a CH3 on the left, a hydrogen on the right, that's what you're going to draw. If you see a CH3 on the left and an H on the right, that's what you're going to draw. And you're just going to keep working your way along the molecule until you get to the other end. All right, you're welcome. And I'm just going to go ahead and put it back and respond to emails. So I'm still here, but again, please feel free to post questions in the chat. All right, so for the discussion board, which way are you turning it? Let me bring up the discussion board. So for the Newman projection here, since you're looking down from the third to the fourth carbon, you're going to turn it to the left. Or I'm sorry, you're going to turn it to the right. So you're being asked to look from this carbon to this carbon, so you can turn it so that this carbon faces you, and the back carbon, the fourth carbon, is behind it. So this is what you're trying to look at. So you've got the molecule as drawn, and you're going to rotate it so this is front and center, and the fourth carbon is behind it. Now, if you were asked to go from fourth to third, you'd turn it the other way. But from your point of view, it looks like you're turning it to the right. Come on, there we go. If we answer the discussion board wrongly, can we go back and change it? I remember you said we were allowed to final exam, but I want to make sure. Yes. So with all the discussion boards, both Chem 1, Organic 1, and any of the online courses I'm teaching, you're always free to go back until the day final exams start to correct your answers for full marks. So particularly if you're like, you have a really busy week, you got a lot going on, you're like, I just don't have time to answer this, just put for attendance and you come back at any time. Now, the reason I cap it the final exam week, I do have to submit grades at some point. So what I'd like to have done once you start your final exam week is the only outstanding grade you have left is your final exam grades. So there's no like gray areas. There's no like, well, I could still get some points back on the homework. I want you to know what it takes to pass the final. But up until like the night before final exam starts, you're free to resubmit any of your questions. You're welcome. This guy asked about steric versus torsional strain, and do you need to know about it? Big picture, yes, but little details, no. So when we talk about the Newman projections, we talk about what they're used for is they're there to determine basically the energy of a given molecule based on its conformation. So let's say we have our Newman projections, and we've got three possibilities here. And obviously there's more, but we're going to consider three possibilities. So in one conformation, we've got two big groups, A and B, as far apart from each other as they can get. This is the anti-conformation. And then we've got another, now we've got the same molecule, but now we've rotated it so that B and A are actually close to each other. And then we've got one where B and A are eclipsed. So what causes these things to be higher in energy? Well, this is the lowest energy, second lowest, and this is the highest. What causes that? And there's lots of ways we can describe it. The easiest way to describe it is sterics. So what happens is that A and B take up space, and when they get close to each other, they start pushing off of each other. Now, this can basically manifest in what's called torsional, or what else did you call it? Steric or torsional strains. Basically, in order for these to get closer and closer together, we had to apply a force on that bond to make it turn. Now, let's consider here our yellow and red atoms. In order for them to be close to each other, get rid of the other parts, a force has to be applied to get them up there, because otherwise they would much rather not be near each other. So when we go to 6 degrees, they're far apart, but really the lowest energy is going to be when they're far away. So this is what the energy is we're talking about when we say that there's a high energy or a low energy conformation. A high energy conformation is one where you get the steric torsional strain due to the fact that they would really like to push away from each other. They really like to be anti to each other. And in order to keep them next to each other, you need to apply a force. That's the strain. Now, that said, I'm saying this like these are radically high energy differences, like one is super unstable, one is not. That isn't really true. They do, it's low enough energy that they actually kind of undergo these like they go these conformational rotations all the time at room temperature. Now, there is a preference. So definitely most alkanes will keep this anti-configuration along each bond because it maximizes energy difference. But we can take these molecules. This is kind of why I like these kits, is because they really do give you a feel for what actually goes on. You can see how I can take this and just kind of bend it around. This is what they actually do in practice. They would like to be stretched out like this, but even stretching out, assuming you don't break a bond, like they're not going to be these perfect anti-conformations. They're going to be kind of floppy. Now, the absolute lowest energy conformation is one where it's completely staggered like this, where everything is anti if you look along the bonds. But at room temperature, they definitely fold in on each other. You definitely get these different structures. You get these different conformations. So when we sit back and say like one's high energy or low energy, we're not talking about like impossible energies here. We're just talking about that it is preferential for you not to be in that type of energy. I don't know a really good example off the top of my head to give you, but that's more or less what this boils down to. So when we say like steric or conformational strains, you just need to understand the big picture here. Because groups around these atoms actually take up space, they push off of each other. And they would like to maximize the distance from each other, and so we usually get staggered conformations. Now, that said, this push is not super, super impossible high energies. We can definitely get eclipse forms, we can get gauche forms at room temperature just fine. This is going to have implications, though, when we start seeing reactions. So there's some reactions that will only occur if the molecule is in a certain conformation. They're accessible, but we do have to supply a little bit of energy to get into that conformation. All right, not seeing more questions. Again, I'm sorry, not seeing more questions now. And as always, these are office hours. These are not lessons. These are not lectures. So if you have questions, please feel free to ask them in advance. I definitely answer email questions at the start, so you don't have to sit through a whole video to get to answer your question. Other than that, have a good weekend, and I will see you all next Monday.